Yeah, okay. So today I'll be talking about temporal graph learning. So so first of all, let me say that so sorry, this was actually a change from the earlier topic, which was on graphs and language models. Yeah, so sorry about this. So it's totally my issue because I had a lot of difficulties with that earlier topic. Yeah, so anyway, if you're interested in that topic, feel free to talk to me offline. But so anyway, let's go on. So this is temporal graph learning. Okay. Yeah. So first of all, so why are we interested in this? So it turns out that in real applications, many graphs are actually temporal. So the reason for this is that generally the graph edges often indicate some kind of interactions. So let's say users interacting with stores or products and things like that. And usually these interactions happen at a particular time. And so this time can often be very important and informative information. So that's why we often like to make use of this information. So there are many examples of this. So for example, here we have a bipartite graph where the users are interacting with items such as news, products, and so on. So this is the case for applications like misinformation detection, fraud, and intrusion detection. So here we have another case where we have just an undirected graph where users are interacting with users. And so this is the case for social networks, citation networks, financial networks, and so on. And then lastly, we can have also a different type of temporal graph, where here we don't have edges which have a timestamp, but actually we have time-evolving node features. So here we see that for each of the nodes, instead of having a single node feature, you actually have a time series where it is evolving over time. So this is the case for sensor networks, such as medical, environmental, or other kinds of sensor networks. So we can still treat it as a special case of temporal networks. So where the only difference is that your node features are evolving over time. Okay, so we will focus on all these type of applications in this talk. But so first of all, let me start by giving some basics of temporal graph models. So some of you may have seen this before, but for the benefit of those who are not, I'll just briefly introduce. So there are many temporal graph models. So these three are some of the most well-known ones, but most of them are based on a reasonably common design approach, which is that what they do is that they feed the edges in temporal order into some kind of neural network module, which is what they refer to as a memory module. So usually it's an RNN-based memory module. And what this module does is that it updates each node's state. Yeah, okay, so what do we mean by state here? So state is just a time-evolving node embedding. So you can think of it as very similar to the standard node embeddings that you're familiar with. So the only difference is that instead of having a single node embedding for each node, we have a time-evolving state. So that means that we have different node embeddings at each time. So that's referred to as the state. Okay, so let's look at this simple example of the graph here. So here we see that our edges are associated with different timestamps from T1, T2, all the way up to T7 in increasing order of time. Okay, so okay. So earlier we said that each node has a state. So that means that for each node, we have some kind of embedding vector. And then as these edges are received from T1 to T7, this state can evolve over time. Yeah, so the simplest way is to imagine that each node's state starts out as the all zero vector. So it starts out as all zeros. So the exact details of the initialization are not so important. So it starts out as all zeros, and then each time a node receives an edge, we make some kind of update to the state. So let's say this node on the top left, it receives an edge at time T1, and then there's some kind of update to the state. And so we can also look at this from the perspective of a single node. So this timeline over here, you can think of it as the edges that are encountered from the perspective of a single node. So let's say we are this node at the center here. So at T3, we encounter an incoming edge. And then at T4, we encounter another edge, and so on. So this is a timeline. And then what happens when we receive each edge is that we execute this memory update module. So this is just some kind of neural network update. So the equations are given here. So if we zoom into what actually happens during this memory update, so this can be shown in the diagram over here. So what happens is that we take in the incoming edge feature, if there exists such an edge feature, so there may or may not be such a feature vector. So this is the feature vector representing the new incoming edge. And then we concatenate it with the neighbor's state. So that means that if we encounter a new edge, then each of the nodes updates itself based on the neighbor's state. Okay, so we concatenate these two informations, and then that is used to update the node itself's state. So in other words, we take the old target node's state, and this is the input to the memory module, and the output is the new target node's state. Okay, so that is how this memory update module works. And so this is the equation over here. So it basically says that the next node's state, so the state of node I at time t, is computed by using the memory update module, taking in the previous state of the same node, so SIT minus, and combining it with the edge attributes, EIJ, as well as the neighbor's previous state. Yeah, and this mem over here represents some kind of module, which usually contains some learnable parameters. And these learnable parameters are updated during the training time. Okay, so that is a just brief summary of the temporal graph learning module. So next, let's talk about some directions and challenges for how we would like to improve this. So the first issue that we want to focus on is the tasks and benchmarks. So it turns out that for these existing models, they are often tested using some relatively simple benchmarks and quite limited benchmarks. So I'll talk more about this. So basically, we would like to think about how more diverse and challenging benchmarks can be designed for this. And so after this, I'll also briefly mention about more powerful learning frameworks. Okay, so let's start with the first one first. Okay, so here's the motivation. So as we know, progress in ML is often driven by high quality, diverse, and challenging benchmarks. So such as ImageNet, OGB, Squad, and so on. So let me just play this video. Yeah, okay. So our goal is to help to develop this kind of challenging benchmarks for the temporal graph learning setting. Yeah, okay. So it turns out that in the temporal graph learning setting, most of the work mainly focuses on two main tasks. And these tasks are the link prediction as well as the dynamic node prediction task. So it's relatively limited. There's not such a wide selection of tasks. And so these are also relatively small data sets. So few and relatively small data sets. So there's no real equivalent of the OGB or Open Graph benchmark. Yeah, so this is the kind of limitation that we would like to address. So how can we design new benchmarks, which, okay, so firstly, we would like to have some real world tasks that can benefit from temporal graph learning. And okay, let me stop this. And they can benefit from temporal graph learning. And so we would like to focus on tasks which are less well explored from the temporal graph learning perspective. And especially, we would like them to involve more complex temporal or graphical patterns. So one of the issues with the existing benchmarks is that people argue that they only use relatively shallow information. So that means they don't really benefit from more complex processing, deeper neural networks and so on. So we would like them to use more complex patterns. Okay, so next I'll talk about what kind of actual benchmarks we have, looked at. I mean, in terms of real world tasks. Yeah. Okay. So the first application is on graph-based fraud detection. So I'll just introduce how the problem works. So the input to the problem is that we are given these transaction tuples, which is of the form of the user, merchant, and time. So this merchant here can be different things. It can be items, products, and so on. But so given this type of tuples, our goal is to identify which users as well as which transactions represent fraudulent behaviors. Yeah, so for this task, for quite long, it was difficult to study this task. And one of the big difficulties was that there's a lack of real-world ground truth labeled data. So, data with ground truth anomalies. Yeah, so fortunately, it turns out that more recently, some data sets with ground truth anomalies have appeared. So here are a few of the ones that I found. So in particular, this Yelp tree is a review fraud dataset, and dgraph is a financial dataset, and this one here is an e-commerce dataset. So, yeah, so as I said, the main benefit is that all of them have ground truth anomalies. So this is quite useful. And so this is just to show the different types of fraud that can be found in this type of data sets. So, collusion, click farming, and so on. Yeah, so in particular, there's a special case of the previous problem of fraud detection that is quite of interest recently, which is cryptocurrency fraud detection. So the benefit of this is that, for these cryptocurrency data sets, everything is public. So we can, we have full visibility on the graph. And so it's also definitely true that there is a lot of fraud involved in this kind of data sets. So here the problem is quite similar. So we are given these financial transaction tuples. So the format of it is from the source account to the destination account. And then usually there are some attributes, such as the amount, as well as the timestamp. And then our goal is, again, the same, to identify which users or transactions represent fraudulent behaviors. Okay, so there are some public datasets. So this elliptic is the most well-used one for Bitcoin datasets. And then, so for Ethereum, there are also a few, but it turns out that there's none that is really ideal. So actually, so one of my students is actually trying to develop, high quality dataset for Ethereum. So this is TBD. Yeah, but anyway, so the main point is that, so we can see that in this type of datasets, they're actually quite interesting and more complex temporal patterns. So as you see here, there's a pump which causes this, increasing pattern followed by a decreasing pattern. Yeah. Yeah. Okay. So there are also other types of attacks that we also would like to detect in this using these temporal graph patterns. So one is the case of computer network intrusion detection. So here the problem is that we are given a stream of source IP, destination IP, and time tuples. So usually they represent users who are connecting to, forming these connections to, such as to a server or something like that. And then our goal is to detect various kinds of attacks, so such as DDoS attacks or various kinds of intrusions. Yeah, so this kind of attack is quite of interest, especially in the industry and so on. And so here are some of the public data sets. So there are various public data sets, but so these two are the ones that are recommended because they have ground truth anomalies, and they also, they are reasonably large, and they also avoid some of the other issues of some of the other data sets. So basically, so here's how the data set looks like. So we have these source and destination IPs. These are happening over time. And then our goal is to detect a set of attackers. Yeah, and then, okay, so there's a final case, which is a little different from the previous ones, which is about anomaly detection in sensor systems. Yeah, so here the difference is that we actually have time series data. So in other words, the node features are actually temporal as well. Yeah, so the motivation is this kind of smart home sensors, autonomous driving sensors, industrial sensors, and so on. And the goal is that we want to monitor this kind of systems against attacks. And so sensor systems are quite a natural fit for temporal graphs, but they are challenging. So in particular, they have very complex correlations or temporal patterns, which cannot really be handled by the existing approaches. Okay, so here's a simple example that we worked on in the past. So this is on anomaly detection in sensor systems. So in particular, we were looking at a certain testbed water treatment plant dataset. So this is how the dataset looks like. So we have this kind of sensors which collect data over time. This is time series data. And then we want to detect this kind of anomalies. So these red regions over here. And so you can see that there are quite complex temporal patterns experienced by the sensors. So so we want to detect these time periods in red where something unusual is going on. And so the public data sets that can be used are this water treatment plant data set, and then this one is a server machine data set. So both of them have ground truth anomalies as well. Yeah, so this is just an example of one of the works that we did. So the goal here is that we have this time series sensor system, and then it turns out that for this particular case, we don't start out with a graph. So we are actually trying to learn the graph as part of the algorithm. So the way we do it is that we first try to learn a graph of the relationships between the sensors. So which sensors are highly related or correlated. And then after that, we use graph neural networks to try to model the data. And in this way, we try to detect deviations from normality. So just a high-level picture of our framework is that we start out with some kind of a sensor embedding module. So the goal of this is to capture the very different behavior of different sensors. So that's because the different sensors can be measuring entirely different things. So some of them can be water pressure, some can be water flow, and so on. So they have totally different behaviors. So we want to capture their different behaviors based on different sensor embeddings. So after doing this, then our next goal is to learn the graph structure. So the way we do that is by trying to predict which nodes are highly correlated in terms of the temporal pattern. So this is learned, in an end-to-end manner together with the rest of the algorithm. And then, so after learning this graph, we use the graph using a graph neural network approach, which is actually a graph attention-based forecasting module. So I won't go into the details, but the high-level picture is that it takes in the past history of the sensors, and then it tries to predict what will happen in the future based on the graph structure. And then finally, we can look at which sensors have a high deviation between the predictions of the model and what is actually observed in the future values. And then those with very high deviations are more likely to be anomalies. So that's why we use this approach to get some anomaly score, and then this allows us to predict which sensors are anomalous. Yeah, so this is just a case study of using this approach. So since we have this graph structure, it is able to localize the region of the graph, so which connected set of sensors are involved in the anomaly. Yeah, okay, so that was just a summary of the tasks and benchmarks. So next I'd like to talk about another goal, which is that of developing more powerful learning frameworks. So in some of the previous speakers, you have heard about expressiveness and so on. So the goal is definitely that we would like to have more flexible and powerful neural networks. So this has been well explored for the static graph case, but for the dynamic graph case, our focus is how we can use the temporal information in a more flexible way. So because our belief is that the temporal information is very informative. So how can we have more expressive frameworks? Yeah, but so it turns out that when we try to do this, one problem that we very quickly encounter is that of overfitting, even using very shallow models. So here you can see some examples. So even when you use a very simple one layer TGN, so TGN is one of the standard architectures. So even for a very shallow and simple module, you can see that there's already a very high level of overfitting. So this is the gap between the training accuracy and the test accuracy. So you can see that in most of the cases, there's quite a large gap. And this gap will only get larger if we increase the number of layers or try to develop even more powerful modules. Yeah, so this is definitely an issue that needs to be addressed if we want to develop more powerful temporal graph models. So how to close the gap between this kind of this training and test. Yeah, so in the case of images as well as like text, data, and so on. So one of the most popular approaches is data augmentation. So it's very popular because it is very simple to implement and very efficient and also very effective. Yeah, so just to give an illustration of this. So let's say if we are trying to do image classification. So one of the popular techniques is cropping. So we would take this red box over here, and then we crop the image usually in some kind of randomized way. And then this produces a new set of images which are in some sense more diverse. Okay, and you can also do a very similar thing for text data. So let's say that we have this sentence over here, the movie was great, and we are trying to do let's say a sentiment classification. So one of the common approaches is TF-IDF based word selection. So TF-IDF is used to select the less informative words. So let's say the word "the" over here, it is very uninformative according to TF-IDF. And so what we can do is to replace it with another uninformative word like "this." So you see here that we replaced "the movie was great" with "this movie was great." And so you can see that this hasn't really changed the meaning of the sentence. So that's why this is a reasonable augmentation. Yeah, okay, so we would like to say, okay, how can we do something similar for temporal graphs? But okay, so one important challenge is that we don't just want to do any data augmentation. We want to do data augmentations that so-called preserve the semantically important information. So what that means is that we don't want to change the essential meaning of the data. So for example, in these images, we don't want to totally crop out the cat in the foreground and just leave the background, because that would kind of ruin the image classification performance. So what we want to do is to modify the image in a way that is semantically unimportant. And so you see the same thing is going on here, where we replace the uninformative words only. So the question is, how can we do something similar for the temporal graph setting? Yeah, okay, so in temporal graphs, we rely on a quite simple intuition, which is the importance of locality. So what do we mean by locality? So there are two types of locality: temporal locality and spatial locality. So temporal locality means that the more recent edges are more informative when making a given target prediction. Okay, so let's just look at this example over here. So you see that we have all the edges with the timestamps. And then, so imagine that we are making a prediction at this node here on the right. So you see that it has two edges attached to it at time T6 and T7. So the edge at time T7 is the more recent one. So that means that this edge should be given a slightly higher importance as compared to the edge at T6, because the more recent edge is more informative. I mean, assuming that we are making a prediction at the final timestamp, that means after T7. Okay, so spatial locality is quite similar, but it means that the information nearby along the graph is more informative for a given target prediction. So once again, let's look at an example of this node here at the top. So you can see that the one-hop neighborhood consists of these two nodes. And so these are the nodes that are most spatially local to the top node, as compared to this node at the left here. It's very far away, so this is less spatially local. So that means that we will want to give greater importance to the nearby nodes as compared to this one. Okay, so how do we do that in terms of the data augmentation? So I mean, how does that relate to data augmentation? So our approach is that we introduce something called adaptive data augmentation. So the meaning of that is that it applies different data augmentation magnitudes depending on the given target prediction. So if we go back to the example we just talked about just now, so imagine that you are trying to make a prediction at this node over here. And let's say you're trying to make a prediction at the final time step, let's say at time greater than T7. So the thing is that based on what we just talked about, we would like to preserve the spatially and temporally local information. That means that the information from these two nodes is spatially local. So we would like to preserve that information. So what that means in terms of data augmentation is that we would like to apply a lower data augmentation magnitude to the very spatially local information. So that means that a lower magnitude should be applied to this close nodes over here, these two nodes here. And a greater data augmentation magnitude should be applied to these further away nodes at the extreme left. That's because we want to preserve the very informative information. And so the same is true for the temporal case. So that means that we want to apply a lesser data augmentation magnitude to the more recent edges like T7 and a greater data augmentation magnitude to these older edges at T5. Okay, so the question is, I mean, that is what we would like to achieve, but it turns out that in practice, there's quite a challenge which makes it difficult to actually achieve that in practice. So the challenge is that, as we have just seen in the TGN model, we actually compute all the dynamic node embeddings in a single forward pass. So it's not like we compute the predictions at each node separately. Right? We actually do a single forward pass, which computes all the dynamic node embeddings at every node. So that means that this makes it very challenging to apply different augmentation magnitudes depending on the given target prediction that we would like to make. Yeah, so this leads to the question of how can we apply different data augmentation magnitudes for different predictions. Yeah, so that leads to this approach, our approach, which is called META, Memory Tower for Adaptive Data Augmentation for Temporal Graphs. Yeah, so there's no connection to the software company. Yeah, but yeah, so the goal here is that we would like to generate, I mean, the way we do it is that we generate a tower of differently augmented graphs where lower magnitude augmentations are applied to the upper layers. Okay, so let's just look at a simple example here. So basically, instead of just having a single temporal graph, so we start out with this single temporal graph, and then we kind of perturb it based on different magnitudes of data augmentation. So a lower magnitude is applied, and then this leads to the level 1 graph, and then a higher data augmentation magnitude is applied, and this produces another graph, which is called the level 2 graph. And so here, this is just a simple example with 2 levels, but in general, you can have more than any number of levels. Okay, so then within each level, what we do is that we apply the temporal graph learning model to that graph. So just apply the TGN model as is on the different graphs. And so the different temporal graph architectures actually have weight sharing. So they share the same weight parameters. And so moreover, the way it works is that we only make the predictions from the top level. So from the top level over here. And so for the lower levels, they are only used to help in the computation. And so the way it works is that for the bottommost level, this extreme bottom over here, the TGN model is applied exactly as in the original form. So exactly without any changes. Okay, but in the upper levels, there is a change then that we need to make, which is shown in this picture over here. So this is called the cross-level propagation. So the only difference is that we, in this memory module over here, so this is almost the same as the memory module we have just shown in the previous slides. So the only difference is that when we pass the neighbor's state to the target node, instead of passing the neighbor's state from the current level, we actually pass the neighbor's state from the lower level. So here, we pass the neighbor's state from level 2, and this is used to compute the target node's state at level 1. So this is exactly what we are showing in this picture here. So we have this memory transition from level 2 to level 1. Okay, so why do we do this? So the goal of this is actually to enforce the spatial locality principle that we have just introduced previously. So the point of doing this is that the nodes at level I receive messages from their neighbors at level I plus 1. So the result of this is that information from more distant neighbors comes from layers which experienced higher magnitudes of data augmentation. So just to return to the previous example, let's say that you are passing messages to this node here at the top. So now, this is the 1-hop neighborhood, the 2-hop neighborhood, and the 3-hop neighborhood. So if you imagine that we have a tower of more than 2 layers, so let's say 3 or 4 layers, then it turns out that the information from the first layer will always come from level 2 of this tower. And then the information from the 2 hop neighbors will come from level 3. And the information from the 3 hop neighbors will come from level 4, and so on. So the point is that by using this design, information from further away neighbors will always come from lower levels of the tower, which means that this information from the lower levels of the tower has experienced higher magnitudes of data augmentation. So this is exactly the goal of adaptive data augmentation that we would like to achieve. Yeah, so the point is that this memory tower allows us to achieve the goal of spatial locality. And so the same is true for temporal locality. So we have a similar approach to enforce temporal locality, which is using something called the memory transitions, which is that the embeddings are periodically transmitted from layer I+1 to layer I. So you can imagine that for a given node, every k number of memory updates, we periodically transmit the embeddings from layer I+1 to layer I. And so the purpose of doing that is that information from further in the past will then come from from lower layers of the tower, which experienced higher magnitudes of data augmentation. So it's basically a very similar idea. Yeah, okay, so this approach can be used to support any type of augmentations that you may want to do on the graph. So it's very flexible. But so in this paper, we particularly used 3 particular augmentations, which are to perturb the timestamps, to remove edges, as well as to add edges with perturbed timestamps. And so we do this in a way that tries to avoid the train test distribution shift. So you may know that data augmentation is generally applied to the during training time, but not during test time. So that means that we would like to do the augmentations in a way that tries to minimize the distribution shift between the training and test time. So in order to do that, we try to design these augmentations in a way that we try to not change the distribution of edge times, and also try not to change the number of edges. So in the paper, we discuss how we achieve these things. Yeah, okay, so here are the experiments. So we experiment with link prediction and dynamic node classification on these MOOC, Reddit, and Wikipedia datasets. And so you can see that basically our meta approach quite consistently improves the performance of the existing approaches, both in the transductive case as well as the inductive case. And so this one over here shows the importance of the adaptive data augmentation. So you can see that when we simply introduce the data augmentation strategies in a naive way, it only leads to a very small improvement in the accuracy of 0.3%. But so when we introduce the adaptive data augmentation, so you can see that there's a significantly bigger improvement in the accuracy. Yeah, okay, so that was for link prediction. So we can also see quite similar results on the dynamic node classification task. So there are also quite consistent improvements, as well as better performance compared to other augmentations. Yeah, and so just now we found that there was a quite severe overfitting of these TGN models. And so here you can see that the use of data augmentation can quite greatly reduce this gap between the training and the test set. So here you see that the gap between these two is much smaller than these two. And as well as the final test performance has also been improved quite significantly. Yeah, okay, so that concludes our approach. So basically we design a way to introduce adaptive data augmentation using this tower of graphs, which provides an efficient way of implementing it. And so this is a general approach which can be used for various kinds of data augmentations, different choices of TGN models or augmentations. Yeah, okay, so of course we would like to further develop this in future. So in particular, so one goal is to provide a better theoretical understanding. So there is some recent work which tries to explain that in order for data augmentation to be effective, it should have high affinity as well as high diversity. So affinity means that it should preserve the labels. So we would like to try to use this kind of theoretical framework to better understand why adaptive data augmentation is necessary. And so as well as, since we have greatly reduced the amount of overfitting, we would like to develop more powerful TGN architectures. So as I said, especially focusing on, since we have an understanding of how static graphs can be made to be more expressive, we would like to see, okay, how about the timestamps? So how can we develop more complex functions that use the time information in a more flexible way? Yeah, and so some other possible improvements are like learnable data augmentation, as well as exploring adaptivity for other data types. Yeah, so in conclusion, I think there are many exciting opportunities to bring temporal graph learning to new applications, as those we have seen, as well as to develop more powerful temporal graph models, which can learn more complex temporal as well as graphical patterns found in such new applications. Yeah, okay, yeah, so thanks for listening. Yeah.
Do you have any questions from the audience?
Hi, thanks for the great talk. So I'm very interested about the way you handle the distribution shift, right, between the training set and test set. So instead of the data augmentation, do you think there are any other future direction that can be used to address this temporal distribution shift in the temporal graph?
Okay, yeah. So that's a great question. Yeah, so I think I definitely agree that temporal distribution shift is very important, especially for applications, because quite often we actually want to apply the data to is the future data, right? So when it comes to future data, there's often some distribution shift involved. Yeah, but okay, so while I agree that it's definitely an interesting problem, it also is quite challenging. There's no really nice guaranteed way to handle this kind of temporal distribution shift. So I think, there are some existing techniques like adversarial techniques and trying to so I think also in some cases it also is quite beneficial to make use of prior information. So we want to learn the features which are stable over time. But of course, it's very hard to know in practice what features are stable over time. Yeah, so I think, it's definitely something that requires future development. But yeah, I think so. I don't have a very, very nice answer in terms of techniques. Yeah, but I think definitely we would like to work on it more. Yeah.
Hi, Brian. Thank you for your excellent talk. And my question is simple. Maybe I think the link prediction in your graph is transductive, right? So how do you think about the inductive link prediction?
So this one is both. Yeah. But so actually you can support both transductive and inductive. Yeah. Which one? The first. You mean not this one? Wait. Which one? Sorry, which one are you referring to? Yeah. Oh, I see. I see. Okay. Yeah. Okay. Yeah, that's a good point. Yeah. Yeah. Okay. So it's true that so the main step that is transductive is the sensor embedding. So I think, yeah, it definitely is an issue because, different sensors have different behaviors. So we need to learn kind of the specific nature of each sensor. So I think if we have, if we want to apply it to some new sensors at test time, that is very challenging because we don't know the behavior of the new sensor. So it could be possible if you have some kind of feature-based representation of the sensors. Then this, maybe this feature representation can be used to learn a model which predicts the embedding, and then you can get the embedding at test time and then use that for the inductive prediction. Yeah. So basically, I think so this current model can't do that, but it could be done if you have some additional feature vector of each sensor.
So I think this is really interesting. I mean, largely huge focus on temporal learning specifically here, but I'm curious about your understanding of how often these temporal graph network methods, the ones that involve like this update of memory per edge, tend to compare to, for example, static methods that maybe even static methods that consider snapshots of the dynamic graph. The reason I ask is because I work in industry, and these kinds of temporal methods that adopt kind of like per edge updates, especially if they're multi-layer networks that involve like updating representations of a group of nodes every time an edge comes in, is a fairly expensive operation. And so oftentimes we consider either static snapshots of a graph that we update embeddings on over time, or we just consider the idea of training a model and then maybe updating it every quarter, every so often after a significant amount of time has passed. So I'm just curious, like, do you have ideas or do you have any reference works that kind of point clearly to the advantages of factoring in these types of temporal interactions on an edge level compared to just static models?
Okay, yeah, that's a great question. Yeah, so I think it's definitely interesting. Yeah, so I'm not totally sure, but so I think these temporal group models are probably not so different from what you suggest in terms of having snapshots and then updating the static graph model over time. So I think depending on how the snapshot approach is exactly done, there may be some differences. Yeah, but let me see. Okay, let me think. Yeah, because so for example, let's say if you're doing the snapshot approach, then you may be doing something like a online training or something like that, right? So yeah, I think so. I haven't seen much work exploring that kind of area, like that kind of online learning. Yeah, so I think it's quite interesting, but I'm not very familiar with like